Uh, so first of all, I would like to thank the organizers of this event. I have been learning a lot. I would like to also thank Roberto for giving me the chance to speak here. And don't worry, my time per slide decays geometrically, so I will finish on time. So I will talk a bit about change point detection. And I will present the mathematical framework, which I did in my master thesis in São Paulo with my advisor, Florencia. She's a statistician, and two geneticists, Tabitha and Renan. So Tabitha and Renan, they had a problem in applied genetics and population genetics, and they used a standard tool to solve the problem. And Florencia and I thought that we could use change point detection to tackle the same problem, right? So another approach to an applied problem. And so today, I will not delve into the details of the problem in genetics. I will just rather present the mathematics we developed to try to solve the problem, okay? So, and simply put, change point detection is the field of statistics which studies abrupt changes in stochastic processes. So you have a stochastic process occurring along a dimension, and then somehow its law changes. So a simple example is you have like a time series for which the first observations follow a certain distribution. For instance, we are IID, normal 0, 1. And then at an unknown time, it changes its parameters. So it changes to 5 and 4. And then and continues under that law for a certain time. And then again, then it changes again for another parameters, all right? So the basic setup is quite simple. You have a family of distributions, right? So we are considering the parametric case here. And we have a change point set, which just consists of an ordered numbers on the unit interval. And we are given n samples of a stochastic process measured at integer times, satisfying the following. The samples inside the intervals defined by the change points follow a certain distribution f theta I star. And of course, two consecutive parameters are different in order to make sense to talk about change. So what is changing here is the parameters from this family of distributions, okay? And they don't necessarily need to be IID, or you need to have independence between blocks, between segments. You could think, for instance, that you have like the first segment is a Markov chain with a certain transition matrix, and then the second one, you change the transition matrix, all right? So you can have dependence within the intervals and between intervals, so on and so forth. And of course, that the statistical problem is to estimate the number of change points, K star, the change point set itself, C star, and the parameters, okay? And of course, study the verb properties, consistency and empirical and asymptotical behavior. So change point detection is a broad framework, right? You can combine it with random graphs. We've seen examples here of the construction of sequential random graphs, right? So you could assume that at first the random graph is constructed by a certain process, and then at an unknown time, this process changes, and you want to know which time it occurred and infer something about each parts of this process, okay? So I explained the usual setup for change point detection, and in the usual setup, you have a single time series. So you have a single series, and you have your number of samples increasing. And so you could think of the traditional setup as you have a signal in the interval 0, 1, which is undergoing changes. And when you increase the sample size, what you're actually increasing is the sampling rate. So you're getting finer, you're getting more samples at this interval. And in our case, we need to adapt a bit that setup, because the inspiration comes from the problem in genetics. We have any individuals from the population. So instead of having only one series, we have n series, and it's the number of series that is growing. And each individual from the population has its own time series. In this case, it would be the DNA sequencing data for each individual. And here it is really fixed. We cannot increase, we cannot get better resolutions of DNA, this DNA sequencing data, okay? So we assume that the random variables are between different blocks are independent, and we also assume independence between different time series here, okay? So, of course, that in practice, this assumption, the assumption of independence between individuals might be too strong, especially if you have like father and son in the same sample, then it certainly does not hold, but depending on their sample, independence might be workable, okay? And the thing is that every individual, so the series, the DNA sequencing of these individuals, they share the same stochastic structure, which is undergoing changes. And in our case, the change points are integers rather than integers in between 1 and m rather than points in the unit interval. And they configure the ending of the blocks, all right? And the goal is the same. It's to infer the number of change points, the change point set itself, and the parameters, okay? So our approach to estimating these quantities is very standard. It's based on likelihood. So let X be the observed data. The observed data will be a matrix, right? The n by m matrix, in which the rows are growing. And let C and theta be the parameters of this model, okay? So the log likelihood is very straightforward. It's just the sum over the samples, sum over the blocks, and the log likelihood for each of these blocks, okay? So we will assume that if you fix C, you can compute the maximum likelihood estimated for theta, and it is well-behaved. Well-behaved in the sense that it is consistent. It will converge to something, all right? And if you do so, and whenever you encounter theta, you plug theta hat, the maximum likelihood estimator, then you can write the log likelihood only as a function of C. So whenever I see theta, I just plug the maximum likelihood estimator, considering that C is fixed, okay? And you will see that theta will fade away from the notation because we are really interested in C. So henceforth, our effort is in estimating C properly, right? Trying to estimate C the best we can, okay. But as is usual with models with nested parameters, when you have models of simpler complexity and of higher complexity, and these ones kind of already describe what is described in the simpler ones, maximum likelihood overparameterizes the model. So Andressa talked about the same phenomena in stochastic block models. She told you that if you just consider maximum likelihood, it will try to find the maximum number of communities. Here, it will try to put as many change points as it can. So in order to avoid that, a standard approach is penalized likelihood. And we just consider here minus the log likelihood just to put in the framework of minimizing a cost function. It doesn't really matter that much, but. And here is the regularization term. It's a positive constant, which you could incorporate in either R or J, but we leave it out because in practice, it is usual to use data-driven methods to choose lambda somehow. We have a regularization that depends only on the change point set. In principle, it could depend on theta, but in this case, it depends only on the change point set, and a regularization on the sample size, okay? And both of these functions are positive. Okay, so of course, that the penalized likelihood estimator will be the set that minimizes this function, all right? And the maximum likelihood estimator for theta And the estimator for theta will be the maximum likelihood estimator associated with this change point set. So it might be straightforward to notice that this is a discrete optimization problem, which is of exponential complexity in M. And albeit M is fixed, it's quite large in practice, right? So we can't brute force our way to compute this. And hence, we need a way to compute it more efficiently. And in order to do so, we assume that the regularization function on the change point set is additive, meaning that there exists a function rho such that the regularization for the change point set is just the sum of the regularization for each change point interval. Okay? The intervals defined by the change points. So under this assumption, we can rewrite the penalized likelihood itself as an additive function. So the penalized likelihood becomes the sum of penalizations on these change point intervals. And of course, that this depends on the data, right? But I have omitted it here on the notation. Okay, so by doing so, what do we gain by doing so, right? So if we denote Ci to be the set of all change points up to variable I, we can define Fi to be the optima of the segmentation up to that variable. And of course, that the solution of the problem is Fm. So the optima of the problem is Fm because Fm, you get all the variables and you want the best segmentation overall, okay? And under this additive assumption, what we get is a recursive equation for F and also for the change point sets. You can compute the sets in a similar manner. And it's easy to see why this recursion holds. So you have your data here, right? It's 1 to M. And you want the best segmentation up to I, up to variable I, okay? And you're calling this optima Fi. So if I tell you that the last change point in this best segmentation is C, so fix C for now, and if I tell you that C is the last change point in this segmentation, then then this optima would be written as the regularization on this interval, which is, since it is additive, it becomes this, right? Plus the regularization here, which is just Fc by definition. And to get the recursion, you just notice that one of them has to be the last change point before I. So you just take the minimum and you have this recursive equation. And with this recursive equation, you can use dynamic programming, which is basically storing data in memory to efficiently solve recursive equations to get an OM squared algorithm. There is also a complexity here to compute like the sufficient statistics, right? It really depends on the model you are working with. Like in those examples with the Gaussians, you can just compute the mean and the sum of squares. And this will be the sufficient statistics. So the sufficient statistics for the blocks, just a combination of those. And so it would be Tnm would be something like n times m. And this gives us the exact estimator, right? So we have the exact solution for that optimization problem. So now that we can compute it somewhat efficiently, the next question is to know if it is any good, right? And one way to attempt to answer that question is by studying the consistency of the estimator. So in order to prove the consistency, we need some assumptions. So first we assume that there exists a limit function L star, which goes from the set of all change points to R, satisfying the following. So for any change point set C, if we normalize the empirical likelihood, the empirical log likelihood by 1 over n, it will converge to this limit log likelihood, and it is why it is called limit log likelihood, okay? And moreover, we assume that this limit function evaluated at the true change point set is strictly greater than this function evaluated at any change point set which does not contain the true one. So this is a condition to guarantee that we are not underestimating the model. Because if C does not contain C star, it means that you forgot a change point. The algorithm forgot a change point. And we are showing that it will not. Like this assumption will guarantee that it will not forget a change point, okay?
So I guess you're stating a very general result, right? As you said, you want your models, I mean, the F, theta I to be very good, right?
Yeah.
I mean, but I guess if you had independent data, probably this would come as a consequence of some property of your parametric set.
Yeah, so, yes, I mean, I can put like strong hypothesis and prove my theorem. The difficult part is showing that something satisfies the assumptions, right? But we did that. So what we did was actually, we were studying like some families and doing like this only for those families. And we noticed like a common structure arising. And then we put this common structure in a general form. And then we showed that they satisfy this common structure, right?
Yeah,
so
that makes perfect sense. It just
mm-hmm.
I'm guessing this is very natural if you're working with just independent data, change point, limited number of change points, everything should be perfectly fine, right?
Yes.
Yeah.
Yes, especially in our case that the resolution is fixed.
Yeah.
I mean, if you have only one time series and then you are increasing the sampling rate, then things are a bit more complicated because, well, you need to certain assumptions on, you know, how large are the proportions of the change point, of the change point interval, so on and so forth. So yes, it's a bit more complicated. In our scenario, is a bit simpler. And if there is dependence, we haven't actually proved that a family which contains dependency on the block satisfies these assumptions, but I think it's doable. But we haven't verified, all right? I will talk about the families we verified these assumptions for. So this is a condition on underparameterization. It's guaranteed that you are not forgetting any change point. And this is a condition for overparameterization. It's basically stating the following. So we assume that there exists a sequence or a function, Vn, which is going to infinite, and its growing is lower than n, satisfying the following. If any change point set contains C star, then we eventually can bound the difference of the log likelihoods, the empirical log likelihoods, by this sequence, okay? And the theorem is quite simple after the assumptions are stated, so assume that the assumptions are met. We assume that the regularization function satisfies the following. If C contains C prime, then the regularization on C is greater than the regularization on C prime. This is basically stating that we are penalizing more complex models. It's basically saying that. And we have to assume that the penalization on the sample size grows faster than Vn and slower than n, okay? So there is a window to choose like a penalization function on the sample size. So under these assumptions, we can show that the estimator is consistent, okay? And the proof is really simple. So basically, you want to show that the C star is the minima of that function eventually. And so the difference between the penalized likelihoods is just the difference between the log likelihoods and the difference here. You can factor these two, the difference between the regularizations. So if you are under the if you are on the underestimation scenario, you can just normalize by n. Since Jn grows lower than n, this will go to 0. So this will converge to this limit function evaluated these two sets. And this, by assumption, is strictly greater than So this is strictly greater than this, so this will be negative. Therefore, the penalized likelihood on C star will be smaller than the other one. So for overestimation, if we assume that C contains strictly C star, so we can just apply the assumption. So we can bound this by plus or minus this. This will probably be, it will be positive actually, but doesn't really matter because since C contains strictly C star, this will be negative. And since J grows faster than Vn, this will go actually to minus infinite, so eventually it will be negative, okay? So the proof under such strong assumptions is quite straightforward, right? The part that you have to write down a lot of things, so a lot of paper is involved, is actually verifying the assumptions, okay? So we were able to verify the assumptions for 3 different families. And so random variables with finite, taking finite values, okay, to a finite number of values. So normal with unknown mean and known variance, so the same variance for everyone, but you have shifting means, and normal with unknown mean and variance. And as I said, I'm presenting the results in the reverse order. So we were studying these families. We noticed some common structure arising, and then we abstract this structure, and then we verify that they meet this structure, the assumption that we just stated. And in all cases, that lower bound for the penalization is log n, which comes from the law of the iterated logarithm, all right? Okay, so this is the dynamic segmentation, because it comes from dynamic programming, the paradigm to solve recursive equations. But it's still inefficient computationally in practice. So in DNA sequencing, we are dealing with huge volumes of data, and m squared can be infeasible in some cases, all right? So the question is, can we, instead of computing the exact solution, can we obtain an heuristical, greedy solution that is faster and still provides a good estimation, right? So in this problem, there is a quite natural one, which is based on the time-owed binary segmentation, binary search, all right? So consider an integer interval from R to S. We will assume again that the regularization is additive. So I did not remark, but on the previous theorem, we don't need the regularization to be additive. Yeah, I mean, we need it to compute efficiently the estimator, but if you put a regularization that is not, and you brute force your way to the exact solution, then it will still be consistent. But here, we really need the additive assumption, even for the consistency. So previously, we defined the penalized likelihood for a change point set. Now we are defining it in a weird notation for integer intervals. So this here, this minus the log likelihood here, is just, you could think of the log likelihood without doing any splits on that interval, right? You just restrict your matrix to that block, and you compute the log minus the log likelihood, okay? And this is the regularization term for that interval. Okay, so for any point C in that interval, we can define the cost of splitting that interval at the point C, okay? So it's just the cost of this interval, R to C, plus the cost of the interval C plus 1 to S, okay? And we use the convention that the penalization of the empty set is 0, so that this function h evaluated at S is the cost of doing no splits at all, okay? So the algorithm is basically, here is the pseudocode, but I think that a picture is worth 1,000 lines of pseudocode. So the idea is quite simple. So you have your original interval here, okay? So 1 to m, and you start with, here I'm writing AGS for hierarchical segmentation, which is the same idea as binary segmentation, binary search, okay? So we start this with the empty set, but I will populate it. You basically do the following. You search for C hat, which minimizes that split cost, okay? So let's say that you get C hat equals C1 here for this interval, for the whole interval. All right, so what you do next is you call this function recursively. So now you will have this interval from C1 plus 1 to M, and 1 to C1. You add C1 to the change point set, to the estimated change point set, and you proceed. So you search again. Let's say that you get C hat equals C1. So you stop, because when the best one is the last one, it means that doing no splits is the best decision. That minimizes the cost, okay? So let's assume that for this one you get C hat equals C2, okay? And again, you do the procedure recursively. You call it recursively again. So C2, C2 plus 1, M. And let's say that you stop here, right? So you stop at this 2, okay? Then you would get this estimated change point set. Of course, that you will get K hat equals 2, right? And then you estimate, actually, you will already have done it to evaluate the cost, but you will get also the parameters, right? The maximum likelihood parameters for theta. So it's quite straightforward, the construction. And again, under some assumptions, we can prove that this greedy algorithm is also consistent. So the idea is similar. I will not delve into details here, but the idea is similar. You basically need to show that with high probability, when there are no change points, assume that we did everything correctly here, okay? So these are the true change points, okay? So you need to show that when there is no, you need a condition to guarantee that when there is no change point in an interval, it will halt. And when there are change points, it could have more than one, right? So here is C2. So when there are more than one, when there are at least one change point in the interval, it will choose one of them, okay? So we need two conditions to guarantee that. They are in the same spirit of the previous theorem, okay? And so under these assumptions and similar assumptions for the growth rate of the penalization and the regularization on the change point intervals, you can show the consistency of this greedy estimation, the greedy estimator, the hierarchical segmentation. Okay, so verifying the assumptions for this, verifying these assumptions is, I put hard here, but it's not quite hard. It's just I couldn't do it. Maybe it's easy, but I couldn't do it, all right? So verifying it directly. So instead, we proved some lemmas which imply the conditions on the assumption, right? So instead of proving the conditions on the assumption directly, we prove the conditions of the lemma, and then they imply the assumption which we need for the theorem. So we did it for the same families. And the same thing for the lower bound on the growth rate. It's log n from the law of the iterated logarithm. So computation-wise, the worst case scenario is the same of the hierarchy of the dynamic programming, but we can show that asymptotically this will be the computational complexity, and this is smaller than m squared, right? So k star is at most m minus 1, okay? So it's k star m, and it's somewhat easy to show that because the number asymptotically, the number of recursive calls is exactly this. So 2k star plus 1. So here, k is 2, so we have 5 recursive calls of the algorithm, okay? And since in each call, recursive call, you do at most m comparisons, because m is the length of the greatest of the whole data, then you get that bound for the complexity. And in practice, it's much faster than dynamic programming. So in practice, you want to use this greedy estimator, okay? But of course so we proved that they're both consistent. And the next question is, okay, but how worst is this compared to the other one, okay? So we do not have a theoretical answer to that question, okay? What we have is the simulations, which is quite straightforward to do. And okay, so comparing the two estimators. So for this, here I have sampled, like I consider 10 change points, 100 variables, so the number of columns is 100. I fixed lambda equals 1. Of course, that in practice you would fine tune it. I fixed Jn with log n, and the regularization on the change point sets, just the cardinality, all right? And like delta here is the minimum difference of two consecutive parameters. So in some sense, it is measuring how hard it is to detect, the hardest to detect change points. So delta is defined as this, right? So of course that we don't have like the theoretical bounds. We do not know if it depends on this quantity, right? It probably depends on complicated stuff, like the more complicated stuff, like on the size of the change points and so on and so forth. But intuitively, you could think that this is related to the convergence, because if two consecutive parameters are quite close, then it would be hard to detect that change point. You would need more samples to detect it, right? Because the signal, the distributions in the blocks are quite similar in some sense.
Are you dividing by n when you divide it? Oh, no, sorry, it's the parameters, right? Sorry.
Yeah, it's the parameters. So in this case, Exactly. So in this case, I consider IID Bernoulli's, very simple scenario. So this would be the difference between two consecutive probability parameters, okay? All right, so I considered sample sizes going from 50 to 500, and for each sample size, I considered 100 data sets. The parameters are fixed across all data sets, all right? And here we have a comparison between the two algorithms. The red one is the exact solution. The blue one is the approximate solution. And here is the Jacquard index, which is just the cardinality of the intersection over the cardinality of the union, right? So since they are consistent, it should be going to 1. And it's quite clear that the approximate solution, the greedy estimator, is worse than the exact one, all right? But they are converging, right? They are going to 1. So here is for the Jacquard index. Here is for the number of change points. And it's interesting to see that, at least in this scenario, where they start underestimating the number of change points, right? They could, if we put a stronger penalization on the sample size, they could instead like go to 10 from above, right? So if they would be overestimating the number of change points, then they go to 10. So just to show now what happens if we take delta equals approximately 0.01, as I said, the convergence should be slower. So the box plots are practically collapsing here, right, at a certain value, but they are converging to 1. So if we wait long enough, they will change and go to 1. And the estimators, from a certain point, for sample size greater than 200, they become, they give the same solutions, right? So the box plots are identical, which is a good indication because, as I said, in practice, you want to use the greedy estimator, right? So this is for the Jacquard index. This is for the number of change points. Okay, this is what I had to present. Thank you very much.